Okay, in this sample problem, we're given a particular electric potential in a certain region of space. It's defined for us. We're asked to find a couple of things. First, we're asked to find the change in potential energy of a charge that moves in this electric potential. And then we're asked to calculate the electric field at a particular point. Well, let's do part A first. There's a relationship between the potential energy of a charge and the electric potential in the space, namely U is equal to QV. So if we want the change in U, as the particle moves, we just need to calculate the change in V. All right, well, let's do that to start. Let's find the potential at the origin, x equals y equals z equals 0. If I just look at the expression for the potential up here, I can see that the voltage is going to be equal to 0 at the origin. And the reason for that is if I just plug 0 into z, y, and x in the expression, I get 0. Now what about the voltage at x equals z is equal to 0, but y is equal to 0.10 meters? Well, note first of all that we were given that y was 10 centimeters. But since the constant is defined in volts per cubic meter, I'm going to work in meters in order to retain consistent units. Okay, at this point I can just write down the numbers. V is equal to V naught, which is 10 volts per cubic meter, times Z cubed is going to be equal to 0, minus 0.10 meters cubed for the Y term, and plus 0 for the X Z term. When I put all the numbers in, I find that this position is 10 to the minus 2 volts. So now, what's the change in U? Well, I'll pop in the value for Q. U is equal to Q, delta U is equal to Q delta V. Value for Q is 750 nanocoulombs. And I put in the change in voltage. So we started at 0, and then we went down 10 millivolts. So that means that the change is a negative 10 to the minus 2 volts. That means the change in the potential energy is equal to 7.5 times 10 to the minus 9 joules. And the energy decreased. It went from a higher potential to a lower. Okay, now that we've done part A, let's go ahead and do part B. Let me write the potential down, just for convenience sake. Take a look at it here. There's a relationship between the electric field and the potential. And that relationship is that the derivative of the potential is related to the electric field, namely E sub x is equal to minus dV dx, and so on and so forth for y and z. So what we can do is we can compute this derivative for the x direction. That winds up being minus 2 v naught x z. Now, at the point that we're evaluating this, x is equal to z is equal to 0, and y is equal to 0.1 meters. That means that Ex is equal to 0. I get this just by putting in the values for x, y, and z into the expression I got for Ex. What about Ey? Well, Ey is equal to minus dV dy. In this case, that winds up being 3 v naught y squared. I can put in the numbers, 3. And we're going to write volts as times the constant, which is 10. Now volts I'm going to write as joules per coulomb per cubic meter, times the value for y. Now I stayed in consistent units, and we can check that. If I perform this multiplication, this winds up being 0.30. And then if I want to check things out, I can note that this is joules per coulomb meter. Well, this is just Newton meters, this is a joule. And so the E field is 0.30 newtons per coulomb in the y direction. What about the z direction? Well, that's just minus dV dz. Again, if I look up, I see that's just minus 3 z squared v naught, which again is equal to 0 at the particular position. So the E field only points in the y direction and has a magnitude of 0.30 newtons per coulomb.